Alright, so this is the third part of reading MLIR paper, and I just realized uh, in part 2 we only read 2 pages, not 3, and I don't know how I feel about that. Alright, so we read up to symbols and symbol tables, and now we're going to continue. We learned about single instruction multiple data streams, SIMD, right? And then we learned about taxonomy, and then we learned about static single assignment, and then what else did we learn about? We learned a little bit about the abstractions that MLIR want to have, and design principles, and if I'm not wrong, the intermediate representation design. So let's just continue and see how far we can get in this video. Alright. Okay, symbols and symbol tables. Operations can have a symbol table attached. This table is a standardized way of associating names represented as strings to IR objects called symbols. The IR does not prescribe what symbols are used for, leaving it up to the operation definition. Symbols are most useful for named entities that not obey SSA. They cannot be redefined within the same table, but they can be used prior to their definition. For example, global variables, functions, or named modules can be represented as symbols. Without these mechanisms, it would have been impossible to define example recursive function referring to themselves in their definition. Symbol tables can be nested if an operation with a symbol table attached has associated regions containing similar operations. MLIR provides a mechanism to reference symbols from an operation, including nested symbols. So we get to dialects. Dialects are a big thing also in LLVM. This can is empty. Great. So dialects. MLIR manages extensibility using dialects, which provide a logical grouping of operations, attributes, and types under a unique namespace. Dialects themselves do not introduce any new semantics, but serve as a logical grouping mechanism that provides common operation functionality, constant folding behavior for all operations in the dialect. They organize the ecosystem of language and domain-specific semantics while following the parsimony principle. The dialect namespace appears as a dot-separated prefix in the opcode. Figure 3 uses affine and STD dialects. This is figure 3. So affine and STD. These are the dialects. These are the namespace in dialects, if I'm not wrong. No, these are the dialects. Okay. The separation of operations, types, and attributes into dialects is conceptual and is akin to designing a set of modular libraries. For example, a dialect can contain operations and types for operating on hardware vectors. Example: shuffle, insert, extract, element, mask. And another dialect can contain operations and types for operating on algebraic vectors. Example: absolute value, dot product, etc. Whether both dialects use the same vector type and where does this type belong are design decisions left to MLIR user. While it is possible to put all operations, types, and attributes in a single dialect, it would quickly become unmanageable due to the large number of simultaneously present concepts and name conflicts, among other issues. Although each operation, type, and attribute belongs to exactly one dialect, MLIR explicitly supports a mix of dialects to enable progressive lowering. Operations from different dialects can coexist at any level of the IR. At any time, they can use types defined in different dialects, etc. Intermixing of dialects allows for greater reuse, extensibility, and provides flexibility that otherwise would require developers to resort to all kinds of non-composable workarounds. Type system. Every value in MLIR has a type, which is specified in the operation that produces the value or in the block that defines the value as an argument. Types encode compile time information about a value. The type system in MLIR is user extensible and may, for example, refer to existing foreign type systems. MLIR enforces strict type equality checking and does not provide type conversion rules. Operations list their inputs and result types using trailing functions like syntax. In Figure 3, std.load maps from the memory reference and index types to the type of the value it loads. From the type theory point of view, MLIR only supports non-dependent types, including trivial, parametric function, sum and product types, while it is possible to implement a dependent type system by combining operations with symbols and user-defined types. Such types will be opaque to the IR. For convenience, MLIR provides a standardized set of commonly used types, including arbitrary precision integers, standard floating point types, and simple comment containers, tuples, multidimensional vectors, and tensors. These types are merely a utility and their use is not required, illustrating parsimony. Functions and modules. Okay, so let's recap this part, which is, I guess, language type system is one of the most important part of the system, of the language. So basically, they have probably integer, signed, unsigned integers, boolean, strings already implemented, but it's user extensible. And from there, MLIR provides a standardized set of commonly used types, including arbitrary precision integers, standard floating point types, and simple comment containers. That's going to be arrays, tensors, tuples, tuples. These types are merely utility and their use is not required, illustrating parsimony. And parsimony is customizability. Functions and modules, similarly to conventional IRs, MLIR is usually structured into functions and modules. However, these are not separate concepts in MLIR. They are implemented as operations in the built-in dialect, again an illustration of parsimony in the design. A module is an operation with a single region containing a single block and terminated by a dummy operation that does not transfer the control flow. Like any block, its body contains a list of operations which may be functions, global variables, compiler metadata, or other top-level constructs. Modules may define a symbol in order to be referenced. Similarly, a function is an operation with a single region that may contain 0 in case of declaration or more blocks. Built-in functions are compatible with call and return operations of the std dialect, which transfers the control to and from the functions respectively. Other dialects are free to define their own function-like operations. Alright, section 4, evaluation, applications of MLIR. MLIR is a system that aims to, this is where it gets very interesting. They finally explain what exactly they intend this new technology for, and well, obviously since this was published in Google, I'm thinking they prioritize the in-house technologies like TensorFlow. So let's continue and get this point. MLIR is a system that aims to generalize and drive a wide range of compiler projects. So our primary evaluation metric is to show that it is being adopted and used for diverse projects. By doing so, we acknowledge the software engineering nature of the problem and contributions. We provide a summary of community activity and describe a few use cases in more detail to highlight the generality and extensibility of MLIR and evaluate how well compiler and domain experts experience the design principles of the IR. Today, MLIR is a growing open source project with a community spanning academia and industry. For example, the first academic workshop about the use of MLIR in high performance computing was attended by individuals from 16 universities and involved 4 national laboratories from 4 different countries. MLIR was also endorsed by 14 multinational companies at the 2019 LLVM developer meeting. More than 100 industry developers attended a roundtable event about MLIR. Community adoption and participation is a proxy measure for usability and need. More than 26 dialects are in development in public or private, and 7 projects across different companies are replacing custom infrastructure with MLIR. We argued that this shows a real need for MLIR, as well as endorses its usability. Alright, well, I was expecting a little bit more technical, but a technical approach, but from what it seems like, there's a good community supporting MLIR, and also there are several different serious teams developing dialects for this project. Alright, so we go from, okay, so now we are A, so I'm thinking we are moving from the parts explaining the technology to its practicality. While the other TensorFlow graphs, while the other discussed representations are familiar to most compiler developments, one of key use cases for MLIR is to support the development of machine learning frameworks. Their internal representations is often based on a data flow graph with a dynamic execution semantics. TensorFlow is an example of such framework. Its representation is a high-level data flow computation where the nodes are computations which can be placed on various devices, including specific hardware accelerators. MLIR is used in TensorFlow to model this internal representation and perform transformations. For the use cases presented in Figure 1, from simple algebraic optimizations to targeting graphs for parallel and distributed execution on data center clusters and asynchronous hardware acceleration, from lowering to a representation suitable for mobile development to generating efficient native code using domain-specific code generators like XLA. Well, that's interesting. What is XLA? Oh, okay, what is XLA? Well, sure, but alright. XLA is a domain-specific compiler for linear algebra that optimizes TensorFlow computation that is designed to improve the performance of TensorFlow models, particularly for machine learning workloads. XLA compiles TensorFlow graphs into highly efficient, low-level machine code tailored to specific hardware architectures such as CPUs, GPUs, and TPUs. Alright, so key features of XLA: accelerated linear algebra. XLA can compile TensorFlow operations on the fly during executions. Optimizing the code as it runs, this allows for dynamic optimizations based on the actual data and computation pattern. This is very interesting. Ahead of time compilation. XLA also supports ahead of time compilation where TensorFlow graphs are compiled into executable binaries before they run. This can be useful for deployment scenarios where performance and startup time are critical. Okay, so ahead of time and just in time, and then we move to hardware specific optimization. XLA generates machine code optimized for specific hardware, leveraging features such as vectorization, parallelism, and specialized instruction set. I'm not recording this over enough, but I'm yawning a lot. Excuse me for that. Fusion of operations. XLA can fuse multiple operations into a single kernel, reducing the overhead of launching separate kernels and improving memory locality. This leads to more efficient use of computational resources. Memory optimization. XLA performs various memory optimizations such as buffer reuse and layout transformations to minimize memory usage and improve cache efficiency. Alright, improved performance. Accelerated linear algebra optimizations can lead to significant speedups in TensorFlow computations, especially for large and complex models. Reduced memory usage. Memory optimizations help in handling larger models and data sets more efficiently. Portability. XLA generated code can be executed on different hardware platforms without modification, making it easier to deploy TensorFlow models across diverse environments. Very interesting. Okay, so we understood XLA a little bit. The representation of a TensorFlow graph in MLIR is illustrated on figure 6. So TensorFlow graph argument, you have a tensor float 32-bit float argument, and then TensorFlow.resource. I'm not getting the exclamation mark, but execution of these operations is asynchronous. The percentage sign control return value can be used to impose extra runtime ordering. For example, the assignment to the variable arg2 is ordered after the read explicitly below. Number 1, control TensorFlow the read variable operation, TensorFlow.resource, TensorFlow.control, TensorFlow.add. Then it goes. So I'm thinking, what are these controls? And then you have probably some forms of functions, and we have like probably 3 statements, which is real 4. Well, these are like dialects, so I'm thinking TensorFlow read valuable operation gets this, gets that, but returns this and this and then this. Oh, interesting. Okay, so this goes to in this, and then you want to add it, and then argument is up here. Yeah, just little code, but the name of the variables are just a little bit funky. Okay, argument 2, argument 0, you get control from here, which is the TensorFlow control. I guess this is just defining what this is doing a little bit, and then fetch 3 control 2, which is a TensorFlow, which is a tensor of float 32-bit, and then TensorFlow control. All right. Okay, so I guess you can define a variable like this in this. I'm not sure if I can call this dialect, but in this dialect. Then this affine, what is affine in CS? An affine frame of an affine space consists of a point called the origin and a linear basis of the associated vector space. Not quite getting that, but okay. Despite the wildly, okay, let's just continue for now. Despite the wildly different abstractions, concurrency, asynchrony, delayed evaluation, MLIR offers the same infrastructure, analysis, and transformation capabilities as for any other dialect or compiler path. In particular, essential graph-level transformations implemented in Grappler. What is Grappler? Are expressible in MLIR for both TensorFlow models and low-level LLVM IR. Dead code node elimination, constant folding, canonicalization. What is how do I get this? Ask it right. What is canonicalization? Okay, canonicalization is the process of converting data that has more than one possible representation in a standard normalized form. This is often used in computer science to ensure consistency, simplify processing, and eliminate redundancy. In the context of compilers and programming languages, canonicalization refers to transforming code. Come on, guys, I love this topic. I might just fall asleep in the middle of it. Canonicalization refers to transferring code or data structures into a standard form that is easier to analyze, optimize, and manipulate. Alright. Polyhedral code generation. Did we get to this part? I'm not sure. We got to canonicalization. Oh, here. Loop invariant code motion, common sub-expression, subgraph elimination, instruction/device specific kernel selection, rematerialization, layout optimization, while other transformations may be domain specific optimizations for mixed precision, operation fusion, shape arithmetic. So canonicalization is the process of converting data that has more than one possible representation. Alright, so where's there there? Give me an example for canonicalization. Excuse me. Alright, considering mathematical, there's two. What happened? Which is a more standardized and simplified form. In the context of programming, canonicalization can help in simplifying and optimizing code. For example, this. Oh, okay. Okay, makes sense. So, as the job of the compiler, you want to be able to do this if it doesn't matter, because then it's less operations. Wow. That's something. One of the original motivations for MLIR was the exploration of polyhedral code generation for accelerators. The affine dialect is a simplified polyhedral representation that was designed to enable progressive lowering while a full exploration of the design points. Here is out of scope for this paper. We illustrate aspects of the affine dialect to show the modeling power of MLIR and contrast the affine dialect with past representations. Similarities. The MLIR affine dialect operates on a structured multi-dimensional type for all access to memory. In the default case, these structure types are injective. Different indexing are guaranteed not to alias by construction, a common precondition for polyhedral dependence analysis. Affine modeling is split into two parts. Affine modeling, two parts. Alright, what are these two parts? These two parts, attributes are used to model affine maps and integer sets at compile time. And operations are used to apply affine restrictions to the code. Namely, affine.for operation is the for loop with bounds expressed as affine maps of values required to be invariant in the function, thus loops have a static control flow. Similarly, affine.if is conditionally restricted by affine integer sets. The bodies of loops and conditionals are regions that use affine.load and affine.store. To restrict indexing to affine forms of surrounding loop iterators, this enables exact affine dependence analysis while avoiding the need to infer affine forms from a lossy lower level representation. Okay, so this piece of code, from what they said, has the for operations. Then we have the load body of affine for loops obey static single assignment. I'm not sure what static single assignment is. Let's use. No, I don't want. What is static assignment? Give me air. Oh, okay. So in SSA form, each assignment to x would create a new variable. Here, x1, x2, and x3 are different versions of the variable x, each assigned exactly once. This makes the data flow explicit and helps in various optimization techniques like constant propagation, dead code elimination, and more. By transforming code into SSA form, compilers can more easily perform these operations, leading to more efficient executable code. Single static assignment is a property of an intermediate representation IR in which each variable is assigned exactly once and every variable is defined before it is used. This simplifies various compiler optimizations and analysis, making it easier to reason about the code. In SSA, if a variable needs to be updated, a new version of that variable is created instead of reassigning the old variable. This leads to a clearer and more explicit representation of data flow within a program. Alright, so basically, to make it better for the compiler to optimize everything, you need to have your variable every time be statically and once assigned. You don't want it to be repeated. Alright. So now we're, I believe, here. So we finished the similarities from the polyhedral code generation. And now we are here. Differences with existing polyhedral. There are numerous. Okay, so what are polyhedrals? Let's get that as well. It's a technique used in computer science for optimizing loop-intensive computations. It involves representing loops and their dependencies in a mathematical structure called a polyhedron. This allows for advanced transformations and sorry, I got an email. Just got distracted for a moment. Okay, so this allows for advanced polyhedral, it involves representing loops and their dependencies in a mathematical structure called a polyhedron. This allows for advanced transformations and optimizations such as loop fusion, loop tiling, and parallelization. In the polyhedral model, loops and their bounds are expressed as linear inequalities. This provides a way to analyze and transform the loopness systematically to improve performance, particularly for higher performance computing and applications that require significant computational power. The polyhedral framework can handle complex loop transformations that are difficult to achieve. With traditional compiler optimizations, it helps in exploiting data locality and parallelism, leading to more efficient utilization of hardware resources. So in the let's read this one more. In the polyhedral model, loops and their bounds are expressed as linear inequalities. This provides a way to analyze and transform the loopness systematically to improve performance, particularly for high-performance computing and applications that requires significant computational power. Alright. That was for polyhedral. So basically the polyhedral thing, I'm not 100% why even had to do that, but okay, differences with exist. Okay, that's why. So there are several differences between the existing polyhedron and MLIR. That's why they wrote this. The MLIR structured memory reference type contains a layout map connecting the index space of the buffer to the actual address space. This separation of concerns makes loop and data transformations compose better. Changes to data layout do not affect the code and do not pollute dependence analysis. Such mixes of transformations have been explored previously but are uncommon. Mix of abstractions. Bodies of affine loops in MLIR can be expressed with operations on type SSA values. Therefore, all traditional compiler analysis and transformations remain applicable and can be interleaved with polyhedral transformations. On the contrary, polyhedral compilers often abstract such details away completely, making it challenging for a polyhedral compiler to manipulate vector types. Alright, smaller representation gap. One of the key features of the polyhedral model is its ability to represent the order of loop iterations in the type system. In this system, a large number of loop transformations compose directly and can be reasoned about using simple mathematical abstractions. However, polyhedral transformations require raising into a representation often drastically different from the original. Furthermore, the conversion from transfer polyhedral to loops is computationally hard. MLIR-based representation maintains high-level loop structure around lower-level representation, removing the need for raising. Compilation speed is a crucial goal for MLIR, as discussed in section 5, but has not been a focus of most existing polyhedral approaches. These rely heavily on algorithms with exponential complexity, on integer linear programming to derive loop orderings automatically and on polyhedron scanning. Algorithms to convert the representation back to loops. The MLIR approach explicitly does not rely on polyhedron scanning since loops are preserved in the IR. In addition, code generation may take place ahead of time. A few examples are when producing generic code for dynamic shapes, or just in time when specializing tensor operations on static shapes. The latter puts stricter constraints on available resources, and both scenarios are important. Experience with the affine dialect shows that first-class affine abstractions facilitate the design and implementation of domain-specific code generators, including the linear algebra dialect and declarative rewrite rules in RISE. Not sure what RISE is. These developments and the affine dialect itself represent important explorations that the MLIR design made practical. Alright, so they're giving us another example. Let me just see how much we got down. Okay, so this is the last page of this video. Experience, I'm not sure, let me just quickly check. I feel like let's do 2 more pages so we compensate for reading 1 less page yesterday. Yeah. Alright, so Fortran IR, the LLVM Fortran front-end Flang, is currently under major development led by NVIDIA and PGI. Similarly to Swift, Rust, and other, Flang needs a specialized IR in order to support advanced transformations for high-performance Fortran codebase, and is using MLIR to support these Fortran-specific optimizations. These high-level optimizations, advanced loop optimizations, array copy elimination, call specializations, devirtualization would be hard to implement using only LLVM. Okay. Okay, so these high-level optimizations, advanced loop optimizations, array copy elimination, call specialization, devirtualization would be hard to implement using only LLVM. For example, FIR is able to model from virtual dispatch table as a first-class concept. Okay. FIR.dispatch table at dtable type. I'm not sure how to read this. This is my first time. I'm not sure even if this is Fortran, but it looks like a LLVM MLIR LLVM dialect. So UV is FIR.alloc, and we have FIR.type, and then FIR.reference. So not quite what is happening here, but if you can see, this is just a function right here, and then just another line. So it says do this, but this type. Not sure. FIR has first-class support for dynamic virtual function dispatch tables. The ability to model the high-level semantics of the programming language in an unstructured IO is very powerful. For example, first-class modeling of the dispatch tables allows a robust devirtualization path to be implemented. While this could have been implemented with a bespoke compiler IR, the use of MLIR allowed the Flang developers to spend their engineering resources focused on the IR design for their domain instead of implementing basic infrastructure. The choice of MLIR also unlocks the reusability of other dialects that are not specific to Fortran. A language-independent OpenMP dialect could be shared between Fortran and C language frontends. Similarly, targeting a heterogeneous platform using OpenACC becomes traceable within MLIR through the sharing and reuse of the GPU-oriented dialects and passes. This is straightforward thanks to MLIR being specifically designed to support a mix of composable dialects. And then section D, domain-specific compilers. The applications above are within large workflows, but MLR also helps building smaller domain-specific compilers. A reusable and modular infrastructure makes these specialized paths feasible and relatively cheap to build. Optimizing MLR pattern rewriting. MLR has an extensible system for pattern rewrites, in addition to statically declared patterns. We had applications where the rewrite patterns needed to be dynamically extensible at runtime, allowing hardware vendors to add new lowerings in drivers. The solution was to express MLIR pattern rewrites as an MLIR dialects itself, allowing us to use MLIR infrastructure to build and optimize efficient finite state machine. Matcher and rewrites on the fly. This work includes FSM, finite state machine, optimization seen in other systems such as the LLVM selection DAG and global ESOL. What is this? Serious. Alright. It's alright. Thank you. Global instruction selection. Global instruction selection is a framework that provides a set of reusable passes and utilizes for instruction selection translation from LLVM IR to target specific machine IR. Global instruction selection is intended to be a replacement for selection DAG and fast instruction selection to solve three major problems. Performance, granularity, modularity, performance, granularity, and modularity. Alright. Okay. Not 100% understanding that, but it's such as this work includes FSM, finite state machine optimization seen in other systems such as the LLVM selection DAG and global instruction selection systems. Well, lattice regression compiler. Lattice regression is a machine learning technique renowned for fast evaluation times and interpretability. The predecessor of the compiler was implemented using C++ templates. This allowed for high performance code with metaprogramming, but expressing general optimizations on the end-to-end models was not straightforward. This particular lattice regression system is used in applications with multiple millions of users, and hence performance improvements are critical. MLIR was used as the basis for a new compiler for this specialized era, which was driven by a specialized search approach, effectively resulting in a machine learning problem being solved during compilation. The resulting compiler was developed by investing a 3% math effort and resulted in up to 8 times performance improvement on a production model, while also improving transparency during compilation. The MLIR design facilitates. Okay, so now we are moving to the consequences of the MLIR design. I'm actually not sure what ML stands for in MLIR, but I hope it's machine learning. Multi-level. Interesting. It is true they say you wake up with assumptions every day that are not true. So it's multi-level, it's not machine learning. It makes sense. It makes sense. Sometimes you're just stupid. Oh God. Okay. Alright, I forgive myself for that. Reusable compiler passes. The ability to represent multiple levels of abstraction in one IR incentivizes the passes that operate across these levels. MLIR handles extensibility by inverting the common approach. Since there are more operations than passes, it is easier for operations to know about passes. This also improves modularity as the dialect-specific logic is implemented within the dialects instead of the core transformations. Since the passes rarely need to know all aspects of an operation, MLIR relies on the following mechanisms to implement generic passes. Operation traits. Many common bread and butter compiler passes, such as dead code or common sub-expression elimination, rely on simple properties like is terminator or is commutative. We define such properties as operation traits. An operation exhibits a trait on conditional example. A standard branch operation is always a terminator for many passes. It is sufficient to know that an operation has a set of traits to operate on. For example, by swapping the operands or removing operations with no side effects and no users for new users. Traits can serve as verification hooks, allowing to share the logic across multiple operations that have the trait. For example, the isolated from above trait verifies that no regions in the operation use values defined in the regions enclosing the operation. It allows for generating processing of functions, modules, and other self-contained structures. Interfaces. When the unconditional static behavior is insufficiently expressive, the processing can be parameterized through interfaces. A concept borrowed from object-oriented programming, an interface defines a view into the behavior of an IR object that abstracts away unnecessary details. Unlike traits, interfaces are implemented by IR objects. Using arbitrary C++ code that can produce different results for different objects. For example, the call operation implements a call-like interface, but different instances of the operation call different functions. MLIR passes can be implemented in terms of interfaces, establishing a contract with any operation that opts into being processed by a pass. Continuing the call-like example, consider the MLIR inlining pass that works on TensorFlow graphs. Flank functions, closures in a functional language, etc. Where were we? Continuing the call-like example, consider the MLIR inlining pass that works on TensorFlow graphs. Flank functions, closures in a functional language, etc. Such a pass needs to know whether it is valid to inline an operation into a given region, and 2. how to handle terminated operations that ended up in the middle of a block after inlining. In order to query an operation about these properties, the pass defines a dedicated interface so that operations may register the implementation with MLIR to benefit from inlining. The inlining pass will treat conservatively. Ignore any ignore any operation that does not implement. I know this is not in an example, but I just say it because it's easier to just go with the flow. That does not implement the respective interface. Constant folding is implemented through the same mechanism. Each operation implements the fold interface by providing a function that may produce an attribute holding the value if the OP is foldable. More generic canonicalization can be implemented similarly. An interface populates the list of canonicalization patterns amenable to pattern rewriting. This design separates generic logic from operation-specific logic and puts the latter in operation itself, reducing the well-known maintenance and complexity burden of instruction combine and people optimizer and the likes in LLVM. Interfaces can be implemented by dialects rather than specific operations, which enables shared behavior or delegation to the external logic. For example, when constant folding TensorFlow operation interfaces are also supported on types and attributes. For example, an addition operation may support any type that self-declares as integer-like with queryable signedness semantics. Dialect-specific passes. Finally, it is valid and useful to define passes that are specific to particular dialects, which can be driven by full semantics of operations in the dialects they are designed for. These passes are just as useful in the MLIR system as they are in the compiler systems. For example, code generators that want to do custom scheduling of machine instructions based on particular machine constraints or other tricks that do not fit into a broader framework. This is a simple and useful starting point for new transformations where generalization isn't required. Mixing dialects together. Okay, so these are basically defining the operation traits, and it goes through interfaces, dialect-specific passes, mixing dialects together. Where's the A section? Reusable compiler passes. Okay, need to know what that is. Water. Alright. I wish I'd use this. Let's go with this one. Alright, so a multi-pass compiler is a type of compiler that processes the source code or abstract syntax tree of a program several times. This is in contrast to a one-pass compiler, which traverses the program only once. Each pass takes the result of the previous pass as the input and creates an intermediate output. In this way, the intermediate code is improved pass by pass until the final pass produces the final code. Multipass compilers are sometimes called wide compilers, referring to the greater scope of the passes. They can see the entire program being compiled instead of just a small portion of it. The wider scope thus available to these compilers allow better code generation, smaller code size, faster code, compared to the output of one-pass compilers at the cost of higher compiler time and memory consumption. In addition, some languages cannot be compiled in a single pass as a result of their design. Interesting. So, source program was lexicon analysis, syntax analysis. You get your abstract syntax tree, you get your semantic analysis, you get your modified SAT, and you move code generation to assembly, and then you go from that to your executable program. Alright. Alright. Okay. So if you have more passes, you will need more compilation handling, but after that it's like you have polished your code better, so it's more efficient and runs faster. Okay, so lexical analysis, just making your tokens. The stage of, okay, so a typical multi-pass compiler has these sections. Relevant information could include things like comments and white space. In addition to removing the irrelevant information, the lexical analysis determines the lexical of the system means the forward declaration is generally not necessary if a multiple. This phase is focused on breaking a sequence of characters with tokens with attributes such as kind, types, value, potentially others as well. Okay, not too bad. Where were we? We're down here. No, we're here. Passes. Compiler pass. Compiler pass. Reusable compiler passes. No, should be here, but not quite sure. Or maybe I just saw it up here. I'm not sure. Because dialect specific, not here definitely. Yeah, we got the interfaces, we got the modules and functions. All right. Consider defined dialect. Okay, we're gonna read again, starting from the C section. Mixing dialects together, one of the most profound but also most difficult to grok aspects of MLIR is that it allows and encourages mixing operations from different dialects together into a single program, while certain cases of this are reasonably easy to understand. Example, holding host and accelerator computation in the same module. The most interesting cases occur when dialects are directly mixed, because this enables an entire class of reuse that we have not seen in other systems. Consider the affine dialect described in section 4b. The definition of affine control flow and affine mappings are independent of the semantics of the operations that are contained in affine regions. In our case, we combine the affine dialect with the standard dialect that represents simple arithmetic in the target independent form like LVMIR. We multiple target specific machine instructions dialects for internal accelerators. Others have combined it with abstractions from other problem domains. The ability to reuse generic polyhedral transformations using OP interfaces to get semantics of operations in specific transformations is a powerful and exciting to us way of factoring compiler infrastructure. Another example is that an OpenMP dialect can be used and reused across a wide variety of source language IRs. Section D. Parallel compilation. An important aspect of MLIR is the possibility to use multi-core machines to increase the compilation speed. In particular, the isolated from above trait, section 5a, allows who's this? Sorry about that. Okay. Indeed, this trait guarantees that SSA use def chain cannot cross the region boundaries and can be processed in isolation. MLIR also does not feature whole module use def chains, but instead references global objects through symbol tables and define constants as operations with attributes. interoperability. Our work involves interoperation with a large number of existing systems, machine learning graphs encoded as protocol buffers, compiler IRs including LLVM IR, proprietary instruction sets, etc. Often the representation has a number of suboptimal or unfortunate decisions that made sense in the context of an existing system, but capabilities of MLIR enable a more expressive representation because importers and exporters are notoriously difficult to test. Test cases are often binary. We want to make sure their complexity is minimized. The solution is to define a dialect that corresponds to the foreign system as directly as possible, allowing round tripping to and from that format in a simple and predictable way. Once the IR is imported into MLIR, it can be raised and lowered to a more convenient IR using all of the MLIR infrastructure, which allows those transformations to be tested similarly to all the other MLIR passes. Okay, so that's gonna be the mark of the end of this video. Still, there's so much I don't know, but I think I'm figuring out as we are going forward. So we finished till here. I feel like one more video to finish this. It's gonna be a 4-video series for this paper, and then after that I will probably need 2 videos explaining everything that we read. So that's gonna be that. Thanks for watching.